very pleased to introduce the next speaker, the second, that's Prinari from University at Buffalo, who will tell us, and he managed to memorize the title, so Maxwell-Bloch system. Previous program in one slide, non-zero background.
Thank you. Thank you so much to the local organizers of the workshop, and this is a lot of everything. Basically being on call 24/7 for any kind of small and big emergencies. All right, so this is joint work with Abeya, who is now the student holding former PhD student in Buffalo, Gino, Greco, Kovacic, and for the very last part, if I get to it, actually Zan participated in the work. She was at UB until this last June as she joined CISTA a short while ago. As Sonia mentioned, this talk is about Maxwell-Bloch systems with homogeneous broadening and one-sided initial conditions. So I'll give you an introduction to tell you what these equations are. We use the inverse scattering transform to solve the initial value problem for these equations, and so I'll briefly discuss the direct problem, the propagation, and the inverse problem. And in the end, I'll discuss the asymptotic states of propagation, and then give you some perspective on current work and future, open problems essentially. So these equations describe the resonant interaction between light and optical media, essentially. In most cases, it suffices to use a description of the interaction of light with the active optical medium, which is semi-classical, where the light is described classically and the medium quantum mechanically. There are a number of assumptions that are made in the process of deriving these equations. One typically averages over the fast oscillations to find the description only in terms of the slowly varying envelopes corresponding to the evolution of the light intensity and phase. Typically, you assume monochromatic light at a single resonant transition. And the resulting equations are called the Maxwell-Bloch equations. They were derived in the late 70s by Maxwell-Bloch and Lamb. What's particularly remarkable is this: when your optical medium is a two-level medium, so two possible states for the atoms, a ground state and an excited state, and for certain three-level media, these equations are completely integrable. They possess a lax representation, a lax pair, and integrability is what makes it possible to linearize these equations exactly using the inverse scattering transform. And this was realized back in the 70s. There is a number of works by Scout and Newell, and then by Zakharov, Kovacic, and Zakharov in the 70s and the 80s, and then some recent work by Kovacic and Minakov, and then I'll mention explicitly work by Peter Miller and Sidali. Another thing that's remarkable is that in spite of all the simplifying assumptions that are made to get to the Maxwell-Bloch equations, these equations are still able to describe a host of physically important effects, such as electromagnetically induced transparency, self-induced transparency, superfluorescence, and so on and so forth. So what are these Maxwell-Bloch equations? The equations are, they're summarized in equation 1. So you have three variables: the electromagnetic pulse Q, which is a complex function of time, and Z. The two-level medium is characterized by a real population density function G, which depends on the physical variables C and Z, and on this parameter K, which I will explain in a moment, and then a complex polarization fluctuation P. These three functions are coupled by the PDEs in one. The Z is the lab propagation distance, time is a retarded time. And the other ingredient, the other thing that appears in these equations is this function G OK, the function g of k is called the inhomogeneous broadening function, and it describes the detuning from the exact quantum transitions frequencies due to the Doppler shift caused by the thermal motion of the atoms in the medium. Typically, one can assume the inhomogeneous broadening function to be a Lorentzian distribution with a width L. And it's easy to see directly from the equations that d squared plus the square modulus p is conserved in time. And so without loss of generality, you can assume it to be, I don't want to mess with this. So I'm just gonna try to hold it if I can.
Right.
Yeah, I was trying to drag it, but it doesn't let me. Okay, let's see. Hopefully I will still be able to switch slides. So without loss of generality, we assume that d squared plus the square modulus of p is 1, which in particular means that d is restricted to be between -1 and 1.
Okay.
Okay,
Yeah,
Oh.
drag the green one.
so it's all right, it's fine. It's fine. Okay, that's good. Okay, so based on what I just said, in a two-level medium, macroscopically, in a two-level system, macroscopically, the medium can be either in a pure ground state, or all the atoms are in the lowest energy level, and this corresponds to taking d equals to -1 and p identically 0. They can be in a pure excited state, so this is a medium with a complete population inversion where all the atoms are in the excited state, and this corresponds to choosing d equals 1 and p equals 0. But generically, you have a mixed state with a fraction of atoms in each of the two states, and in this case, p is non-zero. The assumption is that the initial state of the medium, so the state in the distant past, is assigned. So that's how you prepare your medium. The medium is semi-infinite, so z goes from 0 to infinity. You inject the light pulse at the origin at z equals 0, and then you let it propagate to the right for z positive. And then the Maxwell-Bloch equations describe the optical pulse at each point of the medium at any given time. And of course, you'd be interested in the residual optical pulse along the medium. So what a description of Q for all z at very long times as t goes to infinity, and also the final state of the medium after a long time. So the asymptotic values of the population density and of the polarization as t goes to infinity as functions of z. In particular, this last, so the final state of the medium cannot be assumed to be known. It has to be deduced from the state in the distant past and from the data of the inverse scattering transfer. So couple of additional comments. So that the Maxwell-Bloch equations, as I said, with this inhomogeneous broadening, essentially account for the fact that the atoms' velocities are kind of they change in the medium according to some this inhomogeneous broadening function g of k. An interesting limit is the so-called sharp line limit, sometimes also called the infinitely narrow limit, which corresponds to the case when your inhomogeneous broadening function is taken to be a delta function. And this has been studied a lot in the past and also recently by Lee and Miller and Kovacic and Minakov. In all cases, assuming that the optical pulse decays rapidly as t goes to plus or minus infinity. The reason is twofold. On one end, because the Maxwell-Bloch equations become much simpler when you have when your inhomogeneous broadening function is taken to be a delta function, you get rid essentially of that integral on the right-hand side of the first equation. But there are some drawbacks. that are associated to this limit. Even in the rapidly decaying case. So for instance, one of the drawbacks is that only pure states can be assigned as initial states of the medium if you want to remain in the class of rapidly decaying potentials. As Peter and Sita showed, in this limit, the equations have well-posedness issues unless you impose a causality condition on the optical field. You cannot guarantee uniqueness of solution for the Cauchy problem. And also another thing that Peter and Sita showed is that the optical pulse exhibit slow decay with respect to t for arbitrarily small z, regardless of how rapidly decaying your initial condition is. So we believe that including inhomogeneous broadening not only is a natural physical assumption, but it can also avoid some of the problems, the complications that Peter and Sita highlighted. So as I said, the Maxwell-Bloch equations are integrable. The lax pair is given here. The first equation in the lax pair is called the scattering problem, and that's described by this matrix X, capital X, ik sigma 3 plus q, and the analog of the time evolution is actually a propagation in z, which is given by the second equation, which contains the Hilbert transform of the density matrix rho, which encodes the property of the mediums, the d and the p variables, and the inhomogeneous broadening function g. This calligraphic h is the Hilbert transform. Now, the really nice thing about this is that the scattering problem is exactly the same as for the focusing NLS equation. And therefore, a lot is known and can be just borrowed from existing literature. The only caveat is that here the role of the spatial and temporal variables are switched. So you have t instead of x, and your propagation variable is z instead of time. If you assume q rapidly decaying as t goes to plus or minus infinity, the IDC for this problem was developed a long time ago. Initially, in the original work by Abelitz-Kauf and Newell in 74, the assumption was that they were dealing with an initially stable medium, and then this was generalized by Gabitov, Mikhailov, and Zakharov to the case of an arbitrary initial state of the medium. The case of non-decaying optical pulses as t goes to plus or minus infinity is much more recent. Gino, Gregor, and Gabitov and Sita discussed the case of symmetric non-zero boundary conditions. So your optical pulse has the same amplitude as t goes to plus infinity and minus infinity. What we're interested in is a one-sided non-zero background. So your optical pulse goes to 0 in the distant past, but then it maintains a constant amplitude as t goes to plus infinity for all z. The reason in this audience, the reason for considering this type of problems should be, clear. We want to see dispersive shock waves in this context. We're not there yet, but this is, we hope, the stepping stone to do that. So this one-sided non-zero background combines features of the case of rapidly decaying optical pulses as t goes to minus infinity, and of non-decaying symmetric pulses at plus infinity. In particular, as t goes to minus infinity, the scattering problem reduces to the one of focusing NLS with zero background. As t goes to plus infinity, your scattering problem becomes dt equals x plus dtv equals x plus v, where x plus contains the asymptotic value of the potential q plus. And this matrix has asymptotic as eigenvalues plus or minus psi lambda, where lambda squared is k squared plus a squared, and this a is the amplitude of the background for all as t goes to plus infinity. And there's a standard way to deal with this branching of the eigenvalues. Basically, you introduce a two-sheeted Riemann surface associated to this function lambda of k with a cut along the segment minus IA in the complex plane, and then you introduce a uniformization variable zeta, which is simply k plus lambda, which maps each sheet of the Riemann surface into either the upper half plane of zeta or the lower half plane of zeta. And what's really nice about this transformation is that it's inverted by, so you can write k and lambda as rational functions of zeta, so you can completely remove any branching and express everything in terms of, you know, zeta and one of the zeta. So this is what I was saying. So in this problem, you have four natural regions. You have the interior and the exterior of the circle of radius A in the zeta plane, and in the gray region. So these are D plus minus. D plus is the gray area, and D minus is the white area. And in each of them, the imaginary part of lambda is either positive or negative. So then the ISC actually carries out in kind of a standard way. S equals to minus infinity, you can define eigenfunctions of the scattering problem, which behave like the identity times of, you know, essentially a plane wave. At plus infinity, the behavior is going to be more complicated. It's going to be given by the asymptotic eigenvectors of that matrix X plus times e to the I lambda t sigma 3. And one can show that if the potential is such that, so it's in a 1 essentially at minus infinity, and such that Q minus Q plus is in a 1 at plus infinity, then you can prove that these eigenfunctions, the first column of phi is analytic in the upper half plane of zeta, the second column is analytic in the lower half plane of zeta, and for psi and psi bar, psi is analytic in the region B plus, and psi bar is analytic in the region that I identified as that I call D minus. So altogether, here you have four regions, and so D plus in and out, and D minus in and out. And in each of the four regions, you have a pair of analytic eigenfunctions. So that's a little different from the case of rapidly decaying potentials and also from the case of asymmetric background. But nonetheless, these phi and psi are still fundamental matrix solutions of the scattering problem. And so there's you can relate one set to the other via a 2x2 scattering matrix. In both the rapidly decaying case and the case of symmetric background, typically only the diagonal entries of these S are analytic. Here it's different because each of the entries is analytic in one of the four regions. And the details are there, but it's not really important. So all four entries are analytic in either one of the plus minus in and out. And then you can introduce reflection coefficients. Sorry, this should be R, which is B over A, and R bar, which is B bar over A bar. And take into account the two symmetries of the problem. One is the traditional NLS type symmetry that conjugates the upper half plane of zeta to the lower half plane of zeta, essentially. And but here we have another symmetry, which corresponds to basically switching the sign of lambda, so switching the one sheet of the Riemann surface into the other. And in the uniformization variable, this is a reflection with respect to the circle of radius A. The first symmetry relates the coefficient A bar to A and the coefficient A bar to B, and R bar to R star. Again, that minus should be there. The second symmetry actually relates A to B bar and A bar to B via the optical pulse, the value of the optical pulse at plus infinity. There is a particularly important result to mention, the reflection coefficient. I guess I'm switching between R minus and R, but really these R minus should be R, the reflection coefficient. So one can show that as a result of both symmetries, the reflection coefficient is such that R of zeta times R star of minus a squared over zeta is always equal to -1. And this has two important consequences. One is that no reflection solutions exist. You cannot assume R to be identically zero. In fact, there's more. R is never zero. And this is important in the formulation of the inverse problem. In this framework, the scattering, the discrete eigenvalues appear as zeros of all four scattering coefficients of all four entries of the scattering matrix, and because of the symmetries, they appear in quartets. So you pick one, and then all the symmetric ones follow: zeta n star minus a squared over zeta n minus a squared over zeta n star. For simplicity, we assume that these discrete eigenvalues are simple and finite in number, and we also assume that they're not on the real axis, so that we don't have spectral singularities. But this is just, to avoid complications. If necessary, they can be included in the theory. Finally, you need to introduce normalization constants, norming constants. At each discrete eigenvalue, two of the eigenfunctions are proportional to each other. That's how you get a bound state. That's how you get a function, a solution of the scattering problem that's bounded both as t goes to plus infinity and as t goes to minus infinity. So that means that if you take, for example, psi of A at zeta n, that's going to be proportional to phi at zeta n. So psi is proportional to phi, and so psi of A has a simple pole at zeta n, and therefore its residue can be expressed via this function Cn of z as being proportional to the other eigenfunction that's analytically the same region. And this Cn of z is called the norming constant associated with the eigenvalue zeta n. The norming constants associated to the other elements of the quartet can be obtained from Cn using the symmetries. So I should mention, I said that one important ingredient is the asymptotics of the density matrix. So you can introduce these matrices rho minus and rho plus, which are suitable limits, if you want, as t goes to plus infinity and minus infinity of the density matrix rho, suitably conjugated either with exponentials or exponentials and the given asymptotic eigenvectors y plus. And then denote these the entries of rho plus minus as t plus minus. These give you the asymptotics of D and P, of the population density and of the polarization fluctuation. In particular, D minus and P minus essentially give you the asymptotics of D as equal to minus infinity. At plus infinity, the asymptotics are a little bit more complicated. As you can see, the asymptotic behavior of D at plus infinity in general involves both D plus and P plus, and similarly for P. This has important, so when Q plus is zero, of course, so if you are in the case of zero background, none of this happens, and D plus will give you D and P plus will give you P, but the non-zero background at infinity actually couples this. As far as the propagation of the background is concerned, you can obtain it directly from the second equation of the Lax pair. In particular, you find that Q minus remains zero for all Z, so all along the medium. Q plus has, this constant Q plus at the origin, but then it acquires a Z-dependent phase, which can be explicitly computed in terms of D plus. Also, D plus and D minus can be explicitly computed in terms of, so D plus and P plus can be explicitly computed in terms of P minus and D minus, so the initial state of the medium, and the reflection coefficient that you get from the minus T. So in a sense, this closes the loop. But an important consequence of these equations is that when you have a non-zero background, even if the medium is initially prepared in a pure state, so P minus is zero, here P plus is not zero generically, because it involves R minus, and R minus cannot be taken to be identically zero. So your medium is not going to be in a pure state, even if it starts from a pure state. Not even in the, so there's generically, this is what happens. And then lastly, for the propagation of the scattering data, we can find an explicit expression for the propagation of the reflection coefficient as a function of z. The expressions are actually different depending on whether z is greater than a or smaller than a by in absolute value. But really all you need is one of them because k real is either zeta absolute value greater than a if you are on one sheet of the Riemann surface, or zeta less than a if you are on the other sheet. You can actually solve explicitly this equation, and so you know exactly, you have an explicit formula for the reflection coefficient for all values of z, which is given by this equation 6, which is actually important, and I might mention. And you also have a propagation equation for the known constants. Lastly, the inverse problem can be formulated as a Riemann-Hilbert problem. It turns out that you can introduce a meromorphic matrix valued function using all the eigenfunctions and the scattering coefficients, and then you can express the jump of this meromorphic function m across the real axis through this J1, and J1 is given here explicitly in terms of R minus, the reflection coefficient. Remember, I said it's actually important that R minus never vanishes because that's what guarantees that we don't have, poles in this jump. And then once you solve this Riemann-Hilbert problem, assuming that you can find a unique solution for this problem, which is actually kind of open, then one can reconstruct the potential in terms of the scattering data through that. I'll just take another minute, and this is just to say that if you look at the evolution equations for the reflection coefficient, you can easily, but just by inspection, convince yourself that if a medium is initially in a pure state, the reflection coefficient decays exponentially at large z along the medium. If the medium is initially in an unstable, pure unstable state, the reflection coefficient is actually exponentially growing as z goes to infinity, so growing along the medium. And these has consequences on the asymptotic state of the medium, because from the behavior of R at large z, then you see that if the medium is initially in a stable state, then at large distances, it goes back to d plus is still -1, so the medium will still be asymptotic at large z in a pure state. And if the medium is initially in an unstable pure state, so d minus is -1, now that's the unstable pure state should be d minus equal plus 1. Then because R is growing, then d plus, the final state, will revert back to being initially, to being stable, asymptotically stable, at least for sufficiently large distances. I will not talk about this. I'll just conclude with some open problems. We have a formal solution of the Riemann-Hilbert problem, but the issue of existence and uniqueness of solution for this Riemann-Hilbert problem with non-decaying optical pulses is open. So is the well closeness of the initial value problem with non-decaying optical pulses, and the rigorous study of a long-time asymptotics with inhomogeneous broadening, both for rapidly decaying potentials and for potentials that could, like the ones that were considered, could possibly lead to dispersive shock waves.
Thanks very much.
So it flashed by really fast, but and also you posted something I think today. I saw that. So you have some results about well closures, right?
Yes. So what you showed is that, in the case, in the sharp line limit, even if you start with a rapidly decaying initial condition, your Q, is generic, it's no longer one, for arbitrarily small z, and also, you found this, potentially ill-posedness of the problem unless you impose this condition. What the work that we did with Gino and Zeshwan, we basically generalized the L2 Sobolev bijectivity of the IST by Zhu. He did it for the focusing MLS with rapidly decaying initial conditions. And we showed that this result remains valid also for the Z propagation of this problem, as long as you have an homogeneous broadening. So if you start with an initial datum, which is in H11, then assuming that D minus and P minus satisfy some, mild conditions, you want this, you parameterize D minus and P minus via cosine D, sine D, and P. So if this functions little b and little p admit weak derivatives with respect to K, and these derivatives are at infinity, essentially, then Zhu's result for the focusing NLS goes through. And so we have this bijectivity from H11 to H11. And
So you get some information about how the norm, but it depends on the line width. Is that what you're?
Yes. In fact, this is so we assumed our proof assumes that G is Lorentzian, just so that we could get precise estimates for all those quantities. But the bounds that we find for the reflection coefficient and its derivative, they become singular as the line width goes to 0. And so this could be consistent with what you're finding. We don't have any information about the large Z behavior because that's an open problem.
Thanks very much. Let's thank you again.